Alrighty, welcome back, my friends, to the last video of our segments for lecture 25. Um, so we're going to continue talking about animals and I guess I probably should have said this in one of the previous videos, but how your book has this kind of laid out is we're going to talk chapter 11, which is what we're kind of doing here, is kind of categorizing everything in terms of the living ocean. So location, adaptations, kind of can you swim, can you not, that kind of thing. And then we'll go into primary or plankton and then primary productivity. That's chapter 12. Chapter 13 is going to focus on nekton in particular. So we'll like talk more about those really neat creatures. And then the last or second to last chapter is benthos. So if you're like, oh man, I wanted to talk more about those creatures, like what's going on? We will eventually talk more about them, just not quite yet. So just keeping that in mind. So to finish out our series today, we're going to talk about two factors that limits an organism's ability to live there. And in our next in our next lecture series, which I'll record tomorrow, we'll kind of go further into that and then jump into plankton. So just FYI. So there are many different factors that can influence your ability to live somewhere. Light, basically meaning how far down can sunlight penetrate, and how far is photosynthesis possible. Temperature, warm water versus cold water. And then what we'll continue to talk about, but these are of course factors, are salinity, pressure, buoyancy, inorganic nutrients, and dissolved gases, and the pH. So just like a little note here, because we've already kind of talked at length about dissolved gases when we talked about the composition of the oceans and ocean pH, we're not going to cover those at length. Really, just mentioning them here is going to be about the extent of it, because we've already covered it, right? We don't really need to cover things twice over. Excuse me. So, light. Regarding light, this isn't the first time that we've necessarily talked about light either, but there are other kind of more nitpicky things that we're going to go into. So, as I said at the end of the last video, we break the ocean into various zones, and when we're considering how much light can penetrate down, the euphotic zone would be that there is sufficient light for growth of photosynthetic organisms. And then there's the aphotic zone, which means there's no light penetration at all. And then there's kind of an in-between zone, which we call the dysphotic zone, where there's enough light to during the day to see, but there's not quite enough light to photosynthesize. So it's like, I don't know, think of like when you have your room all dark, but you don't have like blackout curtains, like you still have like some light coming through, say, like your blinds or whatever. It's enough light for you can like to kind of see, especially once your eyes get adjusted, but probably not the best to like cook dinner in, right? Or something like that. I don't know, silly. And then, of course, there are other factors to limitation, which include sun angle, the absorption of wavelengths by water, and the amount of particulates or dissolved organic material in that water. So that kind of goes back, excuse me, to the ideas that we covered before, and like, why is the ocean blue? Because of the wavelengths that are here, or when we talked about light attenuation, and remember that little instrument to see how far down light can attenuate, that Secchi disc, right? And that varies between like the open ocean water and coastal water, right? And sun angle is a huge thing here as well. So at the equator, we have a more direct, straight up and down sunlight, whereas at the poles, it's a much harsher angle, and so there's probably not going to be as much light penetration there. So we've seen these images before, nothing new here, but really just to show On the left here, we're looking at wavelength on the x-axis and depth on the y-axis with the surface here at the top. And the different water types and how far down the various wavelengths and how deep those wavelengths can be seen. So very turbid coastal waters. Think of like the bay itself. Like if you go and look out the bay, it's pretty gross and kind of greenish looking. Then we have moderately turbid coastal water. So this would probably be more like right next to the coastline where you have a lot of wave action, turning up sand, right? Because sand is super malleable, so it's very easily kind of turned around. And then clear tropical water where there's not a whole lot going on in there in terms of things kind of being in the way. You can also think of like that experiment that I did with the sand in the jars and shaking them up, right? It took a while for the fine sediment to settle, but we noticed that we couldn't really see as well through it anymore. And that's what this idea over here on the right is also trying to show in terms of percentage of solar energy on the x-axis and depth on the y-axis, where there's a greater penetration of of solar energy in clear ocean water than in turbid coastal water. Again, just kind of going back to the idea that right along the coast, you have a lot of action with the bottom of the ocean. You're kind of churning up a bunch of stuff. If you have boats and things going in and around, just waves in general. So that's kind of the idea with that. Another adaptation in terms of light is what happens when a creature can light up its skin, which is kind of fascinating, and that's called bioluminescence. So bioluminescence is the light generated by creatures themselves. This is commonly stimulated when the organism is physically agitated. It's common for predator avoidance or luring in prey, or even attracting mates or to see. I mean, it's really quite fascinating. And this picture here is that of a squid. And you can see like the photosynthetic, or not the photosynthetic, the bioluminescent little spackles on this little cutie here, which I think are really, really cool. There's tons of different types of animals that bioluminescence, including plankton, including bigger creatures. You can also think of, again, I know going back to Finding Nemo, but that scene where it was right after the big explosions and lots of things happened, and then it's like you see the light, and that was attracting Marlin and Dory right into that space, and then more chaos ensued until they finally got out of that. But yeah, so you can kind of do one or the other, which is really kind of cool. There's one last adaptation to light, which is really neat, I think, and maybe you've wondered to yourself, like, why do these animals look like that? And it's color changes. So, like this is a Greenland halibut here. You can see how it's kind of speckled and dark on its top, and underneath on their underbelly is completely white. Same thing, similar idea with salmon, right? A darker top of the body and a lighter belly. Similar with rockfish. So the idea with that is that if you're a fishy kind of fishing around and you look down and you see something dark that's blending in with the environment or the bottom of the ocean around them, then you'd be like, oh, okay, well, I smell salmon, but I don't see salmon. And then say you're a fish from underneath and you look up and you're like, can't see anything, because the whiteness of the belly is what it would look like if you were to look up and see sunlight coming through. And so you'd be like, I smell salmon, but I don't see salmon. This is really weird. And then you would just kind of go on your merry way. Similarly as to why great white sharks are really dark on top and light underneath. There's a reason for that. There's a literal evolutionary reason why they're colored in that way, which I think is really, really cool. The last adaptation I want to talk about is temperature. So this graphic here is just showing temperature range in the ocean, really just highlighting the fact that the open ocean has the smallest range between the open, coastal, and the land masses. And with the land having such a crazy, crazy range in temperature, minimum being negative 88 degrees Celsius, no thanks, and a maximum of 58 degrees Celsius. Also very, very hot. So we have terminology for creatures that can withstand a large range and a small range. So stenothermal means that organisms that can withstand a more narrow temperature range. This is generally in the depths of the ocean where there is not really a whole lot of temperature change like at all. And because if you remember, like we looked at those charts, and after a certain depth, like everything kind of evens out and really stays around like 0 to 4 degrees Celsius. So there's not a whole lot of change in the deep open ocean. Whereas euthermal means that organisms can withstand a very wide temperature range, generally in the coastal waters and surface of the open ocean where there's a larger temperature range. Again, kind of depending on location, sun angle, things like that, which would then, of course, control whether or not it's going to be warm waters or cold waters. Some examples of stenothermal creatures could be like coral, right? So coral really only likes a sweet spot between 18 and 24 degrees Celsius. Anything more or less than that can be a little bit much for them. Creatures that can withstand a wide temperature range, a good example would be whales, right? At the surface, there can be warmer waters near the surface, and then they can dive down to the deep ocean to feed or whatever. So you're going from potentially really warm water to potentially really cold water, even when they migrate. Like humpback whales, for example, go down to Cabo in the waters there to mate and to give birth, and then they travel all the way up the California or the Pacific Northwest coastline up to the polar regions to feed in the summer. So just some examples there. And then, of course, and you've probably heard of this before, but cold-blooded versus warm-blooded, basically. So poikilotherms are cold-blooded creatures, meaning that they have no way of regulating their body temperature. Instead, they rely solely on heat conductance. Some examples of that would be invertebrates and most fishes. And we have homeotherms, which are warm-blooded, meaning that they maintain a nearly constant body temperature, usually well above that of the surrounding water. Some examples of that would be seabirds and mammals. So we'll super talk about marine mammals here later on, but something that I think is really fascinating and a little fun factsies about polar bears. Polar bears can maintain an internal body temperature of 98.6 degrees Fahrenheit, which is human body temperature, but they live in the polar regions and they swim in some really freaking cold water. And they, just live in the North Pole. So I just think that that's really crazy. So their fur is so dense that they've been able to evolve to hang out in those really frigid freaking temperatures. So with that kind of wraps up our talk or the video for today. Again, I'm going to make the videos for the next lecture, which would have been ideally today, but I'll make those tomorrow after I have my morning class, just to see how far along in the material that I get with them, because I want to kind of keep everyone on the same page. So thank you again so much for your time and attention, and I will see you all when we return together on Thursday. Thank you.